Let's take a look at precipitation reactions. These are reactions where something is crashing out of solution. Some insoluble substance is separating from that solution. These can be a gas separating from a liquid mixture, or as shown in this example here, they're ever so slowly going to add a drop of lead nitrate into a sodium iodide solution. And watch when the lead iodide precipitates. This is a classic view of a precipitation reaction. In this case, forming this nice canary yellow precipitate. We can write a molecular equation for it, which shows all the substance existing as ionic compounds. And here we are, lead nitrate reacted with the sodium iodide, aqueous, aqueous, forming that lead iodide with the important S there, showing it's a solid. That is your precipitate, and some sodium nitrate that stays in solution. That's fine if they ask for a molecular equation. If an ionic equation is asked for, and this is almost always done just to transition from molecular to net ionic, because what you do, and it's painstaking, is you draw every single ion separated. Lead, nitrate, sodium, iodide, lead, iodide, sodium, nitrate. It all gets spread out. Why? Because it really is remarkable when you look at this. Many of these things show up on both sides. And that truly reflects the actual nature of what's happening. What's really happening is the lead cation is combining with the iodide anions, and it's forming a precipitation. Everything else is just ion soup. It's there on both sides. So in the purest sense, the only thing that's happening is lead and iodide ions are combining to form the precipitate. We call this the net ionic equation. I should point out that this does not mean you can do this chemical reaction. You can't go into the stockroom and get lead ions, but it does show what's truly happening when you mix this solution. The sodium cation and the nitrate anions, since they are not really doing anything, are called spectator ions. Let's go ahead and write another one. Let's go right to the fast method. We're going to react potassium phosphate with calcium nitrate. Potassium being group 1 is going to be always soluble. Nitrate being group 1 is going to be always soluble. I think the precipitate is going to be calcium phosphate, and there it is there. So you could, if you wanted to, write a molecular equation, balance it, which in this case takes some doing. But if they're asking for the net ionic equation, and you know that calcium phosphate is the precipitate, just write the ions from whence it came. In this case, 3 of the calcium ions combine with 2 of the phosphate anions and form the precipitate. See how much faster that is? Let's try this one also and go right to the precipitate, which is going to be the magnesium hydroxide. Would not the net ionic equation just be magnesium cation, 2 hydroxide anions, bada bing, that's your precipitate. So this is much faster. It's not without its pitfalls, however. If there's something that's only sparingly soluble, like this weak acid, hydrogen cyanide, weak acid means it doesn't precipitate much. Should we show it as H plus and Cn minus, or should we together? Scientists decided that since it's over 99% undissociated in a net ionic equation, you should keep it together because that's what it predominantly is. Here is the molecular equation. Hydrogen cyanide plus sodium hydroxide makes sodium cyanide and hydrogen hydroxide, also known as water. The precipitate is water. If you took the trouble of drawing the ionic equation and then the net ionic equation, you'd be good. But I think also you could point out that water's the precipitate, so we are going to form that, but do not separate out HCN because it does not separate out in solution. So here it is shown in all of its detail as a ionic equation. We didn't separate this because it does not ionize, at least not much. But everything else got separated out. Cross out your spectator ions, and there you have your net ionic equation. If you're uncomfortable going directly from here to here, and I could see how you might be, just go ahead and do it the long way. Write your molecular equation, your ionic equation, cancel them out and write your net ionic equation. But if the substance does not ionize, like methanol, for example, don't draw it as being ionized in the net ionic equation.